Welcome to lecture 3 of week 6, which is lecture 28 of Financial Mathematics for Actuary. Today we are going to handle the annuities that are increasing geometrically. Let us set the context why we should study these annuities and then discuss today's roadmap. So, the nature of growth when we are trying to study can be distinguished into two types. One is arithmetic, that is increase by a constant amount, a fixed amount. So, this is where the union wage contract raises by $1,000 a year, where the shape of increase is linear, and we have seen in last two lectures how increasing annuities and decreasing annuities help us in evaluating them. In the that were the content for last two lectures. Today we are going to see the geometric growth. So, this geometric growth is when your salary increases by fixed percentage, 10%, 20%, and once this happens, it actually settles the inflation, or you can consider this situation in terms of stock dividends or tuition fees that are increasing. So, all these things are use cases of this geometric growth where the increase is exponential. In such cases, there is no standard notation as we have for increasing annuities. So, we will just figure out some notation for our purposes. Okay. So, once we have understood or we have set what is our goal, that is to study this geometric growth and how inflation erodes that growth, that also we will keep in our mind, then we can set our roadmap in which we are essentially aiming to value the cash flows that are growing exponentially, and we will also take care of their discounting which is happening exponentially. Okay. So, if you fix this goal, then what is happening is your cash flows are growing exponentially and getting discounted by some other factor, which will be essentially the interest rate. So, in such cases, we need to visualize this tug of war between the growth that is happening and the interest. So, once we understand this visually, then we are in a position as usual to derive the present value calculation for this particular tug of war, for which we will use the tool of geometric series. Once we have understood all these things, then we will master our robust formula and we will avoid few calculator traps related to decimal places, and then we will give you some special cases where we will handle perpetuities or case like k is equal to I, where the growth is same as interest. So, actually there is no growth. All these things are nicely written in Brouwermann's section 2.3 and Chan and Say's section 2.6. So, let us visualize first. Let us come to our first agenda where we are trying to visualize the tug of war between the growth and interest. So, here is the first visual anchor where my money with this geometric growth, our money is growing at the rate of 10%. So, every time you are having 10% increase in the capital. In the first period it will remain 1, in the second period it will grow by 10%, in the third period that grown amount will grow by 10%, and so on, and so we have that compounding effect in play where this geometric growth is happening. However, the buying power of our money is controlled by the interest rate that you are getting, right. So, imagine this growth rate is 10%, but the interest rate is 20%. So, what is happening? Whatever money you are increasing, it is taken down by 20%. So, even if you are having, if you can see those dashed lines, the money is actually increasing, but your present value is actually diminishing. Okay. So, the values are shrinking when you are going in future, right. Okay. So, now what is the takeaway from this? Even if the money grows, if the discounting factor is high, then your present value of money will shrink, and money has time value, right. What if my growth is higher than the discounting that is happening. In such cases, what will happen is you will win, the growth will win, and therefore the final series will actually go to infinity. We call that convergence to infinity, or the series diverges. So, the actual series will grow to infinity, and which is the most likely situation if you are, or most lovable situation if you are earning salary in this form. However, this is not a good situation for employers. So, let us understand this particular tug of war mathematically. Okay. So, we will do the mathematical setup of payment streams where the growth is given to you. So, you have the first payment at time 1, which is 1, and the payments are increasing at the rate of k per period. Okay. So, the first payment will, if the first payment is 1, okay, then the next payment will be 1 plus k. Then the second payment will actually take factor of k as interest, or as the increase on 1 plus k, and the next payment will become 1 plus k square. This is our standard compounding logic. So, in nth period you will have 1 plus k raised to n minus 1. Okay. So, now I have the increasing payment stream which is increasing at the rate of k, right. So, the power of growth always remains t minus 1. At t is equal to 1, it is 1 plus k raised to 0. So, it is 1. Okay. But the factor that will play a significant role is the interest that you are earning on the money, right. So, that is where the present value will be affected. So, what is happening here is the interest rate given is I. So, if I want to calculate the present value of these discounted cash flows which are growing 1 plus k, 1 plus k square and so on, I need to compensate them with the discount factor that we have, which is V, and that will be, if you are looking at the first period, you will multiply by V, which is 1 upon 1 plus I. That is where the present value calculation shows the first 1 plus I here in the denominator. For second period, which is the payment of 1 plus k, I have to discount it by 2 factors. So, that shows 1 plus I squared. 1 plus I k squared will be having a discount factor of 1 plus I cube, and so on and so forth. That is how we have a geometric. So, this particular thing, if you look at the term 1 plus k upon 1 plus I, that should be the common ratio, and then the first term that you will see in this geometric progression is 1 upon 1 plus I, which is our V, and now the common ratio is 1 plus k upon 1 plus I, R. Do we know how to sum this geometric series? In fact, this is how we started our calculations, right. So, we know this, we have done it several times for annuities. So, it is Sn equal to A into 1 minus R raised to n upon 1 minus R. Only when this R is not equal to 1, I am okay. Okay. R should not be equal to 1, this sum is valid, okay, whether it is R less than 1 or R greater than 1. So, let us feed all these values, let us feed all these values in the formula for Sn and see what it comes out to be. So, I have A, which is 1 upon 1 plus I into 1 minus R raised to n, which is essentially 1 plus k upon 1 plus I raised to n upon 1 minus 1 plus k upon 1 plus I. So, this, if you simplify this denominator will be taken here, which will give, so I will just take the denominator. If I take the denominator, this will be 1 plus I minus 1 minus k upon 1 plus I, correct. So, this will cancel off with this one, and I got I minus k upon 1 plus I. But if you look at this 1 plus I and this 1 plus I, they will mutually cancel themselves off. So, what will happen is I will substitute this denominator here, which is I minus k upon 1 plus I. So, I will write it here as into 1 plus I. What is the numerator? You have 1 upon 1 plus I, right. So, this thing is actually getting cancelled with this I will not open up, it is 1 plus k upon 1 plus I raised to n, okay, and this thing will get cancelled with this. So, my new formula will become 1 minus 1 plus k upon 1 plus I raised to n upon I minus k. So, this is my formula for this Sn or the present value that we are discussing. So, I will use this formula and I can generalize it to for payment which is not 1. So, what is my first payment? First payment was 1 here, right. So, I will start with the payment which is not 1. So, in that case I will simply put that formula in to this particular calculator and we design a golden rule which is first payment times that Sn that we derived, Sn is the present value of all the investments that I will be doing or all the payments that I will be receiving. This is the present value, right. So, why this version or why this version of payments, where many textbooks will actually look at the adjusted interest rate J, and we will recommend avoiding this J because it requires complex calculator mode switching, which is too time consuming according to me. The formula that we have derived, the golden rule, works for k less than I or k greater than I for finite n. It does not have any complicated issues. Okay. So, this is one thing. Now, because I am telling you what many textbooks are recommending you to do, I have to explain it why I am telling so. So, let us say if I use the notation j which is used in many textbooks, they will say I minus k upon 1 plus k is j, and then they will imply that this is equal to the present value of 1 upon 1 plus I into annuity due at j for n periods. Okay. So, let us see actually how we get this present value calculation. If you recollect, our present value calculation was something like this. In the first period we had 1 upon 1 plus I, then we had the growth of 1 plus k and which was discounted by 2 time periods which is 1 plus I squared, and then we continued like this, and then in the last period we had 1 plus k and the time factor was n minus 1 upon this 1 plus I was raised to the power n, correct. Now, you look at this value of j which is I minus k upon I minus k upon 1 plus k. Okay. So, we will keep this in mind. We will take a factor of 1 upon 1 plus I out, and then what we have is 1 plus k upon 1 plus I and so on and so forth, which will give me 1 plus k upon 1 plus I raised to n minus 1. Okay. So, now we have rearranged the terms. Now, we need to bring in this j. So, let us look at one trick. We will look at what is 1 plus j. So, if I look at 1 plus j, then it is 1 plus I minus k upon 1 plus k. Okay. So, I can simply simplify this as 1 plus k into I minus k. So, this becomes 1 plus I upon 1 plus k, right. So, now you relate it to this, relate this particular term with this. So, what we have here is actually 1 upon 1 plus j, correct. So, that means I have something like 1 upon 1 plus I into 1 upon 1 plus 1 upon 1 plus j and so on and so forth up to 1 upon 1 plus j raised to n minus 1. So remember this, what is this 1 plus 1 upon 1 plus j? According to our formulation, this is going to be V. V will be equal to 1 upon 1 plus j, right. So this is nothing but the calculation of annuity due for n periods with interest rate j. So I can write this as 1 upon 1 plus I into annuity due for n time periods with interest rate j, correct. So that is how this formulation comes. Okay. But why we are saying that we should avoid this trap? Because now you look at this, you have to calculate j first of all. So you will take two decimals, which is 1 plus k upon 1 plus I, and you will calculate that decimal places. Naturally you will terminate it at some point, correct. And then when you enter your I by y in BA2 plus calculator, you will enter that terminated value. That will lead to many rounding off errors. Also you will have to remember that you have to adjust the annuity type to annuity due, right, and you have to multiply by certain factors. So all these things will lose your decimal accuracy while calculation. So what we suggest is we will stick with the algebra, do not rely on this J logic. Our algebra will be cleaner and safer, and we will do less errors in rounding off. So let us do one problem and see what you get using this rounding off. You can try on your own with the method that we have described through J, or you can try with our recommended method. If so, the problem is I want an inflation proof pension. So if I want a pension of $50,000 at the end of year 1, and then the payment should increase by 3% to match the inflation. I want the pension for 20 years and the interest rate I is 6%. I want to calculate the present value. So our goal is very simple. We will not do these calculations by using the new interest rate J. Okay, so that's the idea. So the inputs that are required for us is what is the first payment, that is 50,000. What is the growth rate that I want, that is 3%. What is the interest rate that is given to me, 6%, and what is the term of the insurance term of the pension that I want to receive. So it's 20. So all these inputs are ready. Okay. Now there are what we need to do, we need to push everything into a present value calculation, correct. So we will do that, and there is a clean formula for present value, which is this, which we have shown, 50,000 into 1 minus the whatever that 1 plus k upon 1 plus I upon I minus k. So we have done that, and now we have this formula. Now you use simple algebra, but if you trim the digits of your decimals, for example, you do 1.03 upon 1.06, and then you recommended places that are shown are 4 places in your BA2 plus calculator, you will inevitably do 0.9717. Then you will raise this to the power of 20, you will get 0.5632. Then you will subtract this 0.5632 from 1, and then you actually calculate this 4368 that is received by 0.03. Remember, I am actually maintaining a precision of 4 decimal places in all these calculations, okay. And then finally I will multiply by 50,000, and the answer comes out to be $7,28,000. Okay. This has a rounding trap. What we will show now is we will use the memory functions of our calculator in an effective manner. So what we will do, we will key in 1.03 divided by 1.06. We will not note down the values. We will use the calculator function x raised to y, and then we will raise this to 20. Okay. This y raised to x is incorrect, it is x raised to y in BA2 plus calculator. So it's you raise this to 20, you store this value using STO button and 1 as a stored value. Then what you do, 1 minus, you recall this value using RCL button. There is no rounding error to a significant number of precisions. Okay, then divide this value by 0.03 and multiply this value by 50,000. So the answer that you will get is 7,20,076.63 dollars. This is where you have not lost because you have rounded off, and it is costing you $76 in rounding off, which may give you an incorrect answer. We have already revealed this trap in one of our lectures where we were losing a lot. Again we are revealing it. So always take care that you are actually using the full strength of your BA2 plus calculator. Okay, so we have covered how to use calculator, how to derive this formula. However, this formula was derived for k not equal to I. How will you do that when k is equal to I, right? Because our geometric sum was not giving any answer for r equal to 1. When k is equal to I, 1 plus k upon 1 plus I is 1. So for that, how will you handle? Okay, if you use this geometric formula, the problem is if the growth rate is k and in discount rate is also, or the interest rate, it is not discount rate, it is an interest rate is also 5%, then our formula actually gives us the denominator to be equal to 0 and the numerator also to be equal to 0. And we get 0 by 0 form where the formula is undefined, correct. So what exactly is happening at those time points? Let us see. When I am dealing with k is equal to I case, if you look at the payment at t equal to 1, which is 1, I am discounting it by 1 upon 1 plus I, fine. But the payment at 2 is again going to be 1 plus I upon 1 plus I square. So it is 1 upon 1 plus I, correct. And that means it is always going to be the discounting factor 1 upon 1 plus I. Okay. So growth is actually cancelling the discount and every single payment has the same present value as the first one, correct. So that means what? If I have n payments, I am simply multiplying n times the present value of the first payment, right. So that's what. So it's basically n times present value of the first payment, which is discounted by one factor. So it is 1 plus I, correct, divided by 1 plus I. So we got a clear cut case where we are actually dealing with k is equal to I case, which is essentially the product of the values discounted for the first payment by one period. That's all. So that's what you will do for k is equal to I. So we handled cases where k is equal to I, k is not equal to I. What if the payments don't end, they will continue forever? That is where we will deal with perpetuities. So those are called geometric perpetuities. Example use case is stock dividends. So what we need to worry about is the factor of 1 plus k upon 1 plus I raised to n, right. So if this factor is less than 1, I am okay, I will have the tail tending to 0 and I will get a finite series. If this factor is greater than or equal to 1, I will have the series exploding series, okay. So it's not going to diverge, it's going to infinity, it's going to explode, okay. So when this factor 1 plus k upon 1 plus I is less than 1, we can quantify that case as k less than I, okay. In that case the fraction is less than 1 and therefore the series will go to 0. This is our same case as when we were handling the perpetuities. So we know the answer. If k is greater than or equal to I, we don't have finite answer. So for the series to have a finite value, I must have I greater than k, otherwise I cannot compute, okay. So this brings us to one famous model which is called Gordon growth model, and when I is greater than k, we will handle that model. The formula will be very much simplified. You have a factor of 1 plus k upon 1 plus I raised to n. That factor will tend to 0, which is similar to our other perpetuities, and that factor will give me this number to be 0, this number to be 0, and it is 1 upon I minus k, which is expected, right. So, this is the real interest that we are getting. So, present value at infinite, present value of infinite time will be the first payment divided by I minus k, that is all, right. So, in corporate finance we use this model called dividend discount model, where if you look at this I minus k, this I had certain meaning and k had certain meaning. K we generally denote by growth rate, and that is called G, and R is the return that I expect from the stock investment. Okay. So, if R is my required return and G is the growth of stock that is happening, then I will simply use the model which is this present value calculation of perpetuities as the dividend that is due the next year, the next dividend that is due, I will use that as D1 upon R minus G, and I will look at whatever estimated price that comes, which is P naught, and if the value is below that or just close to that, we will buy that stock to get the dividends. That is what this perpetuity model will help us in doing that. Okay. Now that we have learnt all these things, let us do one stock valuation problem as active learning. A tech company is actually paying a dividend of $2 next year, which is given as D1. Dividends are expected to grow by 10% per year. Okay. So, the growth rate is given to you 10%, and the investor wants 12% return from this particular stock. What should be the theoretical price of the stock today? Okay. Just try your hand, it is a simple formula, but you need to consider many things, whether I is greater than k or I is less than k, all those things, right. So, just pause the video, solve the problem. On the other side, I will solve the problem for you. Okay, welcome back. You must have tried its simple application of one formula, but before doing that, you have to check the conditions, whether I will get a finite value or not, right. That is what you need to check. So, is it a perpetuity? Yes, because stocks have indefinite life. Is my I greater than k? Returns I want are 12%, and yes, so the k, the growth rate is 10%. So, I have a correct condition which is I greater than k. So, naturally I will apply the formula which is present value is first payment upon I minus k. Okay. So, that should give me an idea of fair price that I will pay for this particular stock. So, what is the first payment? It is $2 upon 0.12 minus 0.10, which gives me 0.02, and that gives me the fair price of this stock to be equal to $100. Okay. So, now that we have done active learning, it is time to summarize what we have learned so far. So, first we have understood the standard case where k is not equal to I, how to calculate this geometric annuity. It is the first payment that will matter, and that will be multiplied by 1 minus 1 plus k upon 1 plus I raised to n upon I minus k. That should give me the present value. The special case for k equal to I, it is nothing special, it is PMT upon 1 plus I multiplied by n. If the payments will last forever, that is n tending to infinity, we are dealing with perpetuity, the present value is PMT 1 upon I minus k. However, this I minus k should be positive. So, that is the essential condition that we need to enforce. If that is not there, then you know what is going to happen, it is going to explode. Okay. So, now what we have done so far and what we will do in the next lecture. So in this week, when we are dealing with varying annuities, the only topic left is varying continuous annuities. So that's what we will discuss in the next class, which is varying continuous annuities, and we will require the knowledge of calculus or the knowledge of integral theory to use this, which we have done several times in past few lectures also. So let us thank you for listening to this lecture, and I will welcome you in the next lecture, where we will discuss varying continuous annuities.